So in this one, we're going to be looking at projectile motion. So number 25, we have a projectile is launched at ground. Turn on the pen. With initial speed of 50 meters per second at an angle of 30 degrees above horizontal, strikes the target above ground 3 seconds later. What is the x and y distances of where it launched and where it landed? So something is launched like this, has an initial velocity of 50 meters per second at an angle of 30 degrees. What is the x and y distances from where the projectile was launched? So eventually it strikes a target above ground 3 seconds later. Okay, so it's going to travel this arc. It's going to hit something, and this was 3 seconds. Time lapse was 3 seconds. Okay, so when you do projectile motion in general, you need to do you want to split your initial velocity vector into two component vectors, the horizontal and the vertical, separately. The vertical would be 50 cosine 30 degrees, and the horizontal would be 50 cosine, and the vertical velocity would be 50 sine 30 degrees. Okay, and what we're gonna do is we're gonna use the kinematic equations and separately. So we're gonna still use this same basic kinematic equation, but we're gonna do it in the x and y direction separately. Now in the x direction, the object there's no acceleration in the x direction. So if I look at just simply this velocity stays constant the entire time. Because unless you assume air resistance or something pushing on the object, the velocity is not going to be changing. So the acceleration is 0. So here we're going to call delta x, let's call it the distance here, big D. I guess we'll call this x. The x distance. The x distance here would be the initial velocity, 50 cosine 30 degrees, times time, 3 seconds, and that would be it. Okay, and so this is going to be 50. Let's see, cosine 30 is root 3 over 2, so 50 times root 3 divided by 2 times 3 is 130. We'll just say about 130 meters. So that's the x distance. The y direction, we use the same equation, and except the initial velocity in the y direction is this one. So the y value is going to be, or the displacement in the y direction vertically is going to be this 50 sine 30 degrees times 3 seconds. But this time, if I say this is if upwards the positive velocity, then I say downward is negative. So we do have acceleration in the y direction, 1/2 negative 9.8 times 3 squared. And I would get 50 times sine 30 is 0.5 times 3 minus 0.5 times 9.8 times 3 squared. I get 30.9 meters. So this target was 30.9 meters above the ground and 130 meters horizontally. Okay, that's what we found. So a ball is thrown horizontally from the top of a 60-meter building and lands 100 meters from the base of the building. So let's just kind of draw our picture here. This is a 60 meters. Lands. Now it's thrown horizontally. So it follows this path, and this is 100 meters. Okay, how long is the ball in the air? This is a fundamental part of projectile motion. Is when you're talking about stuff in the air, it's always the vertical component of motion that tells you this. So we're still looking at this equation. Delta x is v naught t plus 1/2 at squared. Except we're going to look in the y direction. So what do we want to do? I'm going to say downward is positive because it's going to be falling. So I like to just have it, and then I'm going to say rightward is positive. So positive x direction is to the right, and positive y direction is down. So its displacement in the y direction when it hits the ground here is going to be 60 meters. Its initial velocity in the y direction is 0 because it was thrown horizontally. So it has no vertical velocity component at the beginning. and this is a positive 9.8 because I've established down as the positive direction. So t is going to be the square root of 2 times 60 divided by 9.8. .5 seconds. B, what must have been the initial horizontal component of the velocity? Well, if it was so the horizontal direction, whatever velocity it was, it kept it the entire time. And so we use this equation. This delta x would have been 100 meters is equal to whatever its initial velocity was in the x direction times 3.5 seconds. And there's no acceleration in the x direction. So v naught is 100 meters divided by 3.5 seconds. And that gives me 28.6 meters per second. What is the vertical component of the velocity just before the ball hits the ground? Okay, so if I want to know, so at this point it's going to have some component of velocity in this direction. Its vertical component, we can use this equation. V is equal to v naught plus at. Because in the vertical direction it started at 0, and then we know how long it's been in the air for. 3.5 seconds. 34.3 meters per second. D, what is the velocity of the ball just before it hits the ground, including both horizontal and vertical components? Well, the horizontal component of the velocity is the same as it was up here because it didn't change the whole time. The horizontal component is 28.6 meters per second. The vertical component we calculated is 34.3 meters per second. And now we can use our right triangle to calculate both the angle as well as the magnitude. The magnitude of the final velocity is going to be the square root of 28.6 squared plus 34.3 squared by Pythagorean theorem. .7. Okay, and the direction, with like maybe this direction here, we would say is inverse tangent of the y value of the x value. So it's 34.3 divided by 28.6. Now we get trig tan inverse of 34.3 divided by 28.6. 50.2 degrees. Okay. All right. So thanks for watching. If you enjoyed this video, I go through a lot more of these exact kinds of problems with much longer videos on my website. It's entirely free. Check out the link in the description below.